In the previous video, we talked about how the rotating magnetic field is set up inside the stator. This magnetic field is not created from a permanent magnet. It's created from electric current based on the Ampere's law. And the rotation of the magnetic field is due to the temporal variations of the amplitudes of the three-phase alternating current, which is readily available from our electric power system. The three sinusoids of the current are separated by 120 degrees, or 1/3 of the period, and each sinusoid delivers its maximum at a different time. And the magnetic fields created by the three different current phases combine into a single rotating magnetic field. And we derived the rotational speed of the rotating magnetic field, which is called the synchronous speed. And it is proportional to the frequency of the three-phase alternating current, and it is inversely proportional to the number of poles per phase. And this part is probably counterintuitive at first glance, right? It's actually inversely proportional to the number of poles per phase. And we discussed why it is so. So if you increase the number of poles per phase of the current, then you actually reduce the rotational speed of the magnetic current inside the stator. The unit we're using here is RPM, revolutions per minute, right? And you can actually convert this rotational speed to radian per second, right? You just use this formula: 1 rotation per minute equals to 2 pi, right? One revolution is exactly 2 pi radian, right? And then that's done in like 60 seconds. So you divide them. So 1 RPM equals to this many radian per second. So if you want to get the angular speed in terms of a radian per second, then you can use this conversion. Right, basically just multiplying this formula with 2 pi divided by 60. After this rotating magnetic field is set up inside the stator, what is going to be the next sequence of actions, right? So suppose the rotor is stationary at the beginning. So the rotor is not moving; it's stationary, right, at the beginning. The starting characteristics of a typical squirrel cage motor can be summarized in these 5 steps. First, a rotating magnetic field is set up inside the stator using the three-phase alternating current power supply, right? So we have a rotating magnetic field, right? Even though the stator itself is not mechanically rotating, but the magnetic field is rotating at the synchronous speed, right? Second, because the rotor is stationary at the beginning, so there is a relative speed between the rotating magnetic field and the rotor bars. Right? So we're using a squirrel cage induction machine, so the rotor is composed of short-circuited rotor bars, basically. So because the rotor bars are effectively cutting the magnetic flux, which is actually rotating inside the stator, so this kind of a cutting operation is going to induce a voltage in the rotor bars because of the Faraday's law, basically, right? Third, because all the rotor bars are short-circuited, the induced voltage creates large circulating currents flowing through the rotor bars and the end rings, basically, right? Fourth, because the current-carrying rotor bars are immersed inside the magnetic field created by the stator, so each rotor bar is going to experience a strong Lorentz force, right? And fifth, the sum of all the Lorentz forces experienced by all the rotor bars combines into a strong torque, and this torque is going to drag the rotor along in the same direction as the rotating magnetic field. So once the rotor starts rotating and picks up some speed, what is going to what is going to be the next sequence of events, right? Is it going to keep accelerating, or is it going to reach a certain maximum speed and stops accelerating, like reach some kind of equilibrium, right? So remember that the rotational speed of the magnetic field created by the stator is actually fixed at the synchronous speed. So as long as the frequency of the alternating current is not changing, the number of poles per phase is not changing, the synchronous speed is fixed, right? So the rotational speed of the magnetic field inside the stator is constant. It's not going to change, right? It only depends upon the number of poles per phase, which is actually hardwired into the induction machine, and also the frequency of the three-phase alternating current, which is provided by the power lines. So that's not change. That's not going to change either, right? So the synchronous speed is not going to change. So when the speed of the rotor starts to increase, right? Don't forget the rotational direction of the rotor is actually in the same direction of the rotating magnetic field inside the stator, right? So when the rotor starts to accelerate and get more speed, the relative speed between the rotating magnetic field and the rotor starts to decrease, right? Because the rotor is rotating in the same direction as the magnetic field, faster and faster, right? And the magnetic field is not rotating, is actually rotating at a constant speed, right? So the speed difference, or the relative speed between the rotor and the field, is going to decrease, right? The Faraday's law tells us that the induced voltage depends upon the rate of change of the magnetic flux with respect to time, right? So as the relative speed decreases, the rotor bars cut the magnetic field, or the magnetic flux, more slowly, which reduces both the amplitude and the frequency of the induced voltage, right? If the relative speed decreases, the rotor bars is going to cut the rotor bars are going to cut the magnetic flux more slowly, right? Because the relative speed has reduced. So the induced voltage is going to reduce, right? So as the induced voltage reduces, the current, and then the induced Lorentz force, and then the torque on the rotor all reduces, right? And the rotor starts to slow down, right? Because the torque has reduced, right? But as soon as the rotor slows down, the speed decreases, the relative speed between the rotating magnetic field and the rotor increases again, right? Because the rotor has slowed down, so the speed difference between the field and the rotor increases, right? Don't forget, the magnetic field is rotating at a constant speed, right? If the rotor slows down, then the speed difference, or relative speed between the rotor and the magnetic field, starts to increase, right? And once the relative speed increases, the induced voltage, current, Lorentz force, and the torque all increases, right? Once the torque increases, the rotor starts to accelerate again, right? So effectively, the rotor is going to experience this kind of cyclic sequence of events, right? And this cyclic sequence of events all happens during an instantaneous amount of time. It's very, very fast. You cannot actually sort of detect this kind of cyclic behavior. So the overall appearance is that the rotor actually rotates at a speed that is slightly less than the synchronous speed, right? In fact, it is not possible for the rotor to reach the synchronous speed. It's not possible, right? If it did reach the synchronous speed, then the relative speed between the rotor and the magnetic field would be exactly zero. So the rotor bars would not cut the magnetic flux, and no induced voltage would be created at all. So at no load condition, the speed difference between the rotor and the magnetic field inside the stator is actually very small. It's usually less than 0.1% of the synchronous speed. So the rotor speed is just a little bit lower than the synchronous speed under the no load condition. right? If there's no load attached to the shaft, then the rotor is rotating almost at the synchronous speed, just a little bit less. In practice, a motor is actually connected to a load. It's usually connected to a load, right? So the reason for using a motor is to drive some kind of load. So what exactly is the characteristic of the induction machine on the load, right? So we talked about how it's going to start. We talked about how it's going to accelerate, right? But what's going to be the characteristic of the induction machine under load, right? Before talking about that, let's spend some time to understand the torque and the rotational speed of a motor load system, right? So we have a motor here, and then we have a load here, right? And then we have a shaft that's connecting both the motor and the load, right? So let's try to understand the behavior of this particular system, right? So both the motor and the load exert a torque on the shaft. Suppose the load exerts a constant torque, TL, which is in the counterclockwise direction, right? And TL isn't changing with time; it's a constant torque, right? That's the load torque, and it's in the counterclockwise direction, right? And then the motor develops a clockwise torque. Let's call it Tm. That's a clockwise torque, right? And the Tm can be actually varied. We can actually increase or decrease Tm by changing or adjusting the amount of current or electricity actually goes into the motor. So Tm can be adjusted. So at the beginning, suppose the system is at stationary, right? It's not rotating at all, right? At the beginning, and TL actually equals to Tm, right? So Tm equals to TL. Shaft is stationary; it's not rotating, right? So what's going to be the net torque on the shaft, right? The net torque on the shaft is exactly 0 because TL equals to Tm, and they are actually in the opposite direction, right? One is counterclockwise, the other one is clockwise, and the value is sort of the same. So the net torque on the shaft in this kind of scenario is exactly 0, right? And because the system is at a stationary, right, and the net torque is 0, so the system is not going to change, right? It's not going to start rotating or something. It's not going to do anything. It's just going to stay stationary. It's not going to do anything, right? Now suppose we want the load and the shaft to rotate in the clockwise direction with a speed of n1. With a speed of n1. So how are we going to do that, right? So to do this, we're going to increase the motor torque, Tm, so that Tm is going to exceed TL. So Tm is going to become larger than TL, right? So the net torque on the shaft is going to be clockwise, right? Because Tm is clockwise, TL is not changing; it's a constant TL, and we are increasing Tm so that Tm exceeds TL, right? So the net torque on the shaft is going to be clockwise, right? So once we have a clockwise net torque, the shaft is going to start to rotate, right? It's going to get the speed. The speed is going to increase, right? And when the desired speed n1 is reached, when the shaft starts to rotate at n1, at that point, we reduce the motor torque, Tm, to be exactly the same as TL. Right? TL during this entire process, TL is not changing, right? So we increase the Tm at the beginning of the process, right? Now, once the rotational speed of the shaft has reached the n1, we reduce Tm again, so that the value of Tm becomes identical to the value of TL, right? And at this point, Tm equals to TL again, but the shaft is not going to be stationary. It's going to rotate at a constant speed of n1, and the speed is not going to increase and it's not going to decrease. It's just going to be a constant speed, right? Because the net torque is 0, there's no net torque to change the speed anymore, right? We have reduced Tm to exactly equal to TL, right? So there's no net torque to change the speed of the shaft anymore. So the shaft is going to keep rotating at the speed of n1, right? So now suppose we keep reducing Tm, right? At this point Tm equals to TL, right? But let's keep reducing Tm. Let's keep reducing Tm so that it is less than the load torque TL now, right? If that's the kind of case, then TL is going to be larger than Tm, and then we have a net counterclockwise torque, right? And don't forget at this point the shaft is still rotating in the clockwise direction, right? But if you have a net torque that's counterclockwise, then the speed, the clockwise speed is going to reduce, right? The clockwise speed is going to reduce from n1 to 0 gradually, right? And then because the net torque is counterclockwise, then you're going to have a counterclockwise speed, right? After the speed has decreased from n1 to 0, and then you're going to the shaft is going to get the speed in the counterclockwise direction. It's gonna start to rotate in the opposite direction now, right? So when the counterclockwise speed of the shaft reaches another value, say n2, that's our desired value, desired speed, right? We increase Tm immediately so that it reaches the value of TL again, right? And at that point, Tm equals to TL, and then the net torque disappears. Net torque becomes 0, right? And then no net torque to change the speed anymore. No net torque to change the speed anymore. Then the load and motor system is going to reach another equilibrium, and the shaft is going to sort of keep rotating at the constant speed of n2, right? So when the torque developed by the motor is sort of in the same direction as the rotational speed of the shaft, the power, the energy is delivered from the motor to the load. So the motor is driving the load when the torque of the motor is in the same direction as the rotational speed, right? So power actually flows from the motor to the load in this kind of scenario, right? And in this kind of scenario, the torque developed by the motor is actually in the opposite direction of the rotational speed of the shaft, right? And in this kind of case, power actually flows from the load to the motor. The motor is actually receiving energy from the load, right? And in this kind of scenario, the motor is not really a motor; it's actually a generator, right? If you actually convert the energy into electricity, then this is indeed a generator, right? So there is this kind of distinction depending upon the rotational speed and the motor torque are in the same direction or not, right? This is in the same direction, so motor is driving the load, right? But this is in the opposite direction, right? So energy actually flows from the load to the motor, right? The motor becomes a generator. So the conclusion we can draw from this analysis is that when the motor torque is identical to the load torque, the speed of the shaft will not change. But when they are not identical, right, the rate of change in speed, which is the delta n divided by delta t, that's the rate of change. That's the rate of change, right? So delta n is just the changing speed, and this changing speed happens during a time that's delta t, right? So the rate of change in time is delta n over delta t, right? And this rate of change in speed, rotational speed, is proportional to the net torque, and the net torque is motor torque subtract load torque, and then it's going to be inversely proportional to the moment of inertia of all revolving components, right? For simple geometries, this moment of inertia can be actually computed from simple formulas. For really complicated geometries, you can actually get the moment of inertia by summing the moment of inertia of all its components, and each of the components can have a relatively simple shape, right? So that's a very, very important equation, right? the change in speed, or the rate of change in speed proportional to net torque and inversely proportional to moment of inertia. Right. So now, after we have developed a better understanding about the motor load system, let's talk about what will happen if we apply a load to the induction motor. Right. Suppose the motor is initially running at no load, right? No load at all. So this is kind of the scenario at the end of the acceleration stage, right? That's no load. Once we apply a load to the shaft, the load torque increases, and the equilibrium between the motor torque and the load torque is disturbed, right? So the rotor speed is going to decrease because the load torque has increased, right? So the rotor speed is going to decrease. Rotor is going to slow down. So under no load condition, the rotor was rotating in the same direction as the magnetic field, right? So once the rotor slows down, the relative speed between the magnetic field and the rotor starts to increase, right? And once the relative speed increases, the rotor bars cut the magnetic field or magnetic flux more rapidly, which is going to increase the induced voltage and the resulting current in the rotor bars, right? So the Lorentz force increases and the motor torque increases progressively. But when the motor torque reaches the same value as the load torque, we have reached a new equilibrium, and the rotational speed of the rotor is not going to change anymore, right? Because the net torque is now zero, right? If the net torque is zero, nothing is going to change the rotational speed, right? That was the formula that we were looking at, right? If the net torque becomes zero, then nothing is going to change the rotational speed, right? So the rotational speed of the rotor is going to stop decreasing and maintain at a constant level, right? The most important thing for us to remember is that at a state of equilibrium, motor torque equals to load torque. Rotor speed is different from the synchronous speed. It's different from the speed of the magnetic field. The speed is different. The torque is the same, but the speed is different. And the relative speed, or the speed difference, is such that the induced voltage, current, and the Lorentz force produces the needed motor torque that balances the load torque. So that's probably the most important thing for us to understand, right? And at this point, we can introduce another highly important equation for induction machines, which is the definition of the so-called slip. Slip. So the slip, S, is the difference between the synchronous speed and the rotor speed divided by the synchronous speed. So when under no load condition, the rotor speed is almost identical to the synchronous speed, right? It is less than 0.1% of the synchronous speed, right? So it's less than 1/10 of a percent of the synchronous speed. So it's a very, very small difference. And at that point, Ns is almost equal to Nr, right? So the numerator becomes almost zero. It's close to zero. And at this point, the slip is very, very close to zero, right? So under no load condition, slip is almost zero, right? And on the other extreme, on the other hand, right, when the rotor is locked, when the rotor is not rotating at all, it's at a stationary position, Nr equals to zero, right? Which is at the beginning of the acceleration process, which is at the starting point, right? Either when you hold the rotor to a stationary position, or when you actually open all the end rings, so there's no induced current, that kind of thing. So when Nr, the rotor speed, equal to zero, right? So Ns subtract zero equals to Ns. So the relative speed is exactly the synchronous speed, right? So the slip actually equals to 1 under this kind of a scenario, right? So when the rotor is locked at the stationary position, the slip is unity. That's slip, and we're going to use the concept of slip in the following sequence of videos.